In this video, I am discussing KSET Mathematical Science previous year question papers. Here I taken 2023 question paper, topic complex analysis. By seeing this video completely, you can able to solve most of the complex analysis question. See, KSET 2023 question. Which of the following series is absolutely convergent? First, the concept. A series is said to be absolutely convergent. A series is said to be absolutely convergent if the series of the absolute values of its terms converges. That means summation modulus of an is convergent. Here, option A is summation n is equal to 1 to infinity. I taken modulus I raised to n log n divided by n square plus 1. Modulus of I raised to n is equal to 1. Therefore, modulus of log n divided by n square plus 1. If we take log n to the denominator, we write it as 1 divided by n square plus 1 log n whole raised to minus 1. See next. By using Bertrand test, let alpha and beta be any two numbers, then the series summation n is equal to 2 to infinity, because here n is equal to 2 taken because log of 1 is equal to 0. That's why n is equal to 2 to infinity 1 by n raised to alpha log n raised to beta. Series is in this form. Then first condition, if alpha greater than this value, alpha greater than 1, beta is any real number belongs to R, then this series, whole series is convergent. If second condition, alpha less than 1, if this n raised to alpha less than 1, beta, any real number belongs to R, series is divergent. Third condition, if alpha is equal to 1, beta less than or equal to 1, this less than or equal to 1, in this condition, divergent. If alpha equal to 1, this form 1 by n log n square, log n whole square. In this case, series is convergent. Now, given series is here n raised to 2, alpha raised to 2, here alpha greater than, alpha equal to 2 is there. This is greater than 1. Beta belongs to R is there. Therefore, in this condition, series is convergent. Option 1 is this is convergent by using Bertrand test. convergent. Next, we get answer. No need to check other options. But for your practice, I solve all the questions, all the options. See, summation n is equal to 1 to infinity 2I raised to n divided by 1 minus 2I raised to n. Here, necessary condition for series is convergent is if sequence of its limit is convergent and converges to 0. This is the necessary condition. Here, if we take limit for sequence, for this sequence, limit n tends to infinity to I raised to n divided by 1 minus 2I raised to n. If we take 2I raised to n common and numerator, denominator get cancelled, remaining ones. If you apply n tends to infinity, this term becomes 0. Therefore, 1 divided by 0 minus 1 is equal to, modulus of this is equal to 1, not equal to 0. Here, we want 0, but this is not equal to 0. Condition fails. Therefore, this is divergent. Divergent or not convergent. Not convergent. B option, divergent. Next, by Bertrand test. See, if you take modulus, this value become 1. Next, if we take log n denominator, we get this 1 by n log n raised to minus 1. Here, this is alpha, n raised to 1 is there. If beta, here beta is equal to minus 1 is there, this is less than 1. In this condition, beta less than or equal to 1, in this condition divergent. Simply we say by using Bertrand test, this is divergent. Divergent. Bertrand test, this is n is equal to 2 to infinity because log 1 value is 0. Next, C, option C. Option D, summation n is equal to 1 to infinity e raised to I n phi divided by n. We know that e raised to I n phi is e raised to I theta. E raised to I theta. In polar form, we can write it as r cos theta plus I sin theta. If this r e raised to I theta, we can write it as r cos theta plus I sin theta. Similarly, I e raised to I n pi, you can write cos n pi plus I sin n pi is equal to minus 1 raised to n. This becomes 0. Sin n pi becomes 0. Therefore, this cos n pi is equal to minus 1 raised to n. Now, summation n is equal to 1 to infinity minus 1 raised to n by n. It becomes this type. We know that modulus of minus 1 raised to n. Minus 1 raised to n, we get this as 1, summation 1. Therefore, 1 by n by P series test, summation n is equal summation n is equal to 1 to infinity 1 by n raised to p. If p greater than 1, in this case, series is convergent. P less than or equal to 1, in this case, series is divergent. Here, P is less than or equal to 1 case is there, therefore, this series is divergent. Therefore, correct option for absolutely convergent series is option A. Summation n is equal to 1 to infinity I raised to n by I raised to n log n divided by n square plus 1. By using Bertrand test, this is convergent. Next, the power series z raised to n converges for, options are there, modulus of 1 less than 1, modulus of z less than 1, modulus of z greater than 1, modulus of z is equal to 1 for all z. Comment for your answer. What is the answer for this question? Next, see, second question. The set of all z belongs to complex number such that series 1 by 2 raised to n 1 divided by z plus 1 whole raised to n is absolutely convergent. In what condition this is absolutely convergent? See, we can write it as, if we take denominator to numerator, we get z plus 1 whole raised to minus 1 whole raised to n. Here, w is equal to z plus 1 whole raised to minus 1. It is in the form of n is equal to 1 to infinity 1 by 2 raised to n, w raised to n. Here, absolutely, they are asking absolute convergence. This is, if we take absolute convergence, now take this, this becomes an is equal to, here an is equal to 1 by 2n, therefore 1 by 2 raised to n plus 1 into 2 raised to n. If I apply limit, we get 1 by 2. That means r is equal to 1 by r is equal to radius of convergence is 2. 1 by r is equal to 1 by 2. Therefore, r is equal to 2. Here, w is equal to z plus 1 whole raised to minus 1 is there. Therefore, in place of w, we put this value, z plus 1 minus 1 raised minus 1 less than 2. If we take denominator to numerator, sign will less than sign becomes greater than sign. Therefore, z plus 1 greater than 1 by 2. Here, radius of convergence is convergent. Series is convergent. In what condition? If this is less than r. In this condition, r means z naught. Z naught. Modulus of z is less than z naught. In this condition, series is absolutely convergent. But here we are getting modulus of z plus 1 greater than 1 by 2. Therefore, if we take this one to this side, it becomes minus. This is convergent in what condition? In deleted neighborhood of, in deleted neighborhood of, in deleted neighborhood of this, in deleted neighborhood, that means domain minus deleted neighborhood. This point, D minus D, here C is given, C minus 1, 1 by 2. In this case, except this point, this is absolutely convergent. See, where is an option? Option B, C minus, except this point, this is absolutely convergent. Therefore, option B is the right answer. Next, third one. Let P be a polynomial. P of x is equal to summation I is equal to 0 to k a I x raised to I with a k not equal to 0. Then the radius of convergence of the series n is equal to 0 to infinity. P of n z raised to n is, see, is given. Now, let P of n, they are given P of n be a polynomial. We know that radius of convergence is 1 by r is equal to supremum of limit n tends to infinity, supremum of a n plus 1 divided by a n. This is the condition for radius of convergence. Now, if you take an plus 1 as pn plus 1 divided by pn, it tends to 1 as n tends to infinity. Therefore, 1 by r is equal to 1. Here r is equal to 1. We get r is equal to 1. See, where is an option? Option C is the right answer. Now, let series n factorial z raised to n has radius of convergence. Check where this series is convergent. Or else 1 by r is equal to what? Find r value. Radius of convergence value is what? Comment your answer in comment box for this question. Next, fourth question. The principal value of minus 1 raised to I is, see, this is complex exponent or exponential form of complex number. Let z is not equal to 0. That means complex number z is equal to x plus iy. Here alpha belongs to complex number. Then define z raised to alpha is equal to e raised to alpha log z. Now z raised to alpha is equal to e raised to alpha ln mod z, means here ln r. This is ln r. Mod z means r. R is equal to root of x square plus y square. Theta is equal to tan inverse of y by x, means this. Here e raised to alpha ln z plus I argument of z plus 2n pi. Here n belongs to integers. Now we want minus 1 raised to I. Substitute in this formula. Here E is equal to alpha means I is there. I ln of 1 ln of 1 plus I. Argument of z is here. Minus 1 is there. Z is equal to minus 1 plus I of 0. Why here 0 is there? Your x is minus 1 is there. Therefore, value of this is 0. Tan inverse of 0 is 0. Now, we know that log 1 is equal to log 1 value is 1. Log 1 value is 1. Therefore, this is 0. Argument also 0. Now, I 0. This is also 0 plus I 2n pi. We know that I into I is equal to I square is equal to minus 1. This becomes e raised to minus 2n pi. See where is in option? This is minus 2n pi. Minus 2n pi plus 1 given. Minus 2n pi minus 2n plus 1 into pi, n belongs to z. This is the right answer. Now, let z is equal to r e raised to I theta. Which of the following gives a correct multi-valued expression for log z? See, all options are given. What is the right answer for this question? Comment in comment box. Comment your answer in comment box. Next, which of the pairs of paths delta and the function f from delta to closed interval, they are given closed interval delta to c given below in 1 to 4 for integration under the closed curve delta f is equal to 0. With respect to what they not given. Okay. See, this is all question. Concept is Cauchy theorem. If f of z is analytic in a simply connected domain with f dash is continuous in D, then integration under closed curve f of z dz is equal to 0, where C is any closed contour lying inside D. In this condition, it is value is 0. Next, Cauchy-Gorsuch theorem. If f of z is analytic in a simply connected domain D, then integration under the closed curve C f of z dz is equal to 0 for any closed contour D. See, they are given closed contour. If we find poles of this, we get values z is equal to 2i minus 2i outside for this interval. Therefore, its value becomes 0. All if we check all, it it takes some time. Therefore, by using theorem, we can choose correct answer. All 1, 2, 3, and 4 becomes 0 by using theorem. Next, sixth question. Let F from U to C be analytic where Q is a region in C. Which of the following conditions given below, which of the following conditions given below will make the function f constant? Options are given. See concept. Lewis theorem. If f of z is entire and bounded, then f of z is constant. See, they are given analytic and they are given a region in C. Therefore, analytic, in which condition it is, they are asking for constant function. U is equal to C and F is bounded on U. In this condition, F is constant by using this theorem. If f of z is entire and bounded, then f of z is constant. Try this question. If f is analytic and non-constant on D and U is subset of D is open, then f of U is. Options are given. Try this question. Comment your answer in the comment box. Next, seventh question. Consider the function f of z is equal to z minus a whole raised to m g of z, where g of a is equal to 0 for a fixed a belongs to complex number. Which one of the following is false? See, they are telling false. A is 0 of order m. A is 0 of order m for f. A is full of order m for 1 by f. 1 by f has an isolated singularity at A. 1 by f has an essential singularity at A. See the concept. Zeros of f of z definition. A point z is equal to A is called a zero of f of z if f of A is equal to 0. Let's see order or multiplicity of a 0 means if f of A is equal to 0, f dash of A is equal to f double dash of A is equal to and so on, f raised to n minus 1 of A is equal to 0, but f of nth order differentiation, f of nth order differentiation not equal to 0, then z is equal to a is a 0 of order n. Representation z is equal to a, f of z is equal to z minus a whole raised to n g of z, where g of a is not equal to 0 and g of z is analytic. In this case, this order is n. Simple 0 means if n is equal to 1, then z is equal to a is a simple 0. Next, relation to poles. If f of z has a 0 of order n at z is equal to a, then 1 by f of z has a pole of order n at z is equal to a. This is if f of z is equal to 0 of order n, that means g of z, or else f of z is equal to z minus a whole raised to n, 0 of order n, then f of z is equal to 1 divided by z minus a. In this case, 1 divided by f of z is equal to z minus a whole raised to n, has pole of order n at z is equal to a. Next, types of singularities.